We're going to talk about latent heat. What is the word latent mean? What does that mean? Well, it's a word that is used outside of physics, and it means that it's not visible, it's not apparent, something that is hidden, something that is not there. Well, it is there, but you can't see it. That is latent. And why is this called latent heat? Why is this heat called in that way? We're going to see in a second. Latent heat, it says right here, it's the energy absorbed or released by a substance during a change in its physical state. Physical state means when you change from solid to liquid, or from liquid to vapor or gas, or so on. Or also when you change from liquid to solid, when you go back to that, or when you go from the vapor state to the liquid state, it requires energy. And that energy is going to be called the latent heat. But the thing is that when you add all of this energy, the temperature does not change. That's why it's called latent. Because usually when you add energy to a substance, to a material or whatever, you add energy to it, what happens to the temperature? It changes. But not here. When you reach a certain degree of temperature, the temperature, for example, when you reach 100 degrees Celsius in water, it's supposed to be boiling. It's supposed to change. And during that time, while you're adding that energy, the temperature stays the same. So that's the whole thing here. That's why it's latent, because when you add energy to something, it's supposed to be changing in temperature. But in this case, when you reach these parts, these boiling points or freezing points, the energy that you add or subtract, it's not going to change its temperature while it's changing phase or material physical state. And we're going to talk about, for example, let's see this thing. Let's say we have a ice cube that is exactly of 1 kilogram. Here it is. This is a 1 kilogram huge ice cube, and it has a temperature of 0 degrees Celsius. Now this solid of water could have a lower temperature, but right now it's at 0 degrees Celsius. It's ready to become a liquid. And I'm going to be adding energy to it, and I'm going to be adding exactly 330 joules. That is going to be the energy to change all of this 1 kilogram of ice into liquid water. But the thing that is very interesting to see here is that while I add this energy, and while this thing is changing in phase, it looks very different, but you know what? In temperature, it stays the same. So until you get the last piece of ice, it's going to remain at 0 degrees Celsius. So while it starts to it starts to turn into a liquid, this thing is still at 0 degrees Celsius. And when all of this becomes a liquid, it's going to be 0 degrees Celsius. But only until you have the last little piece of ice. After that, this temperature is going to be increasing if you keep on giving it energy. And here's the other example. At the other side of the spectrum, once you have a liquid, you put it on the oven, you make it reach, you give it energy until you get 100 degrees Celsius. Well, you're going to need 2,000 or 2,300,000 joules in order for you to make all of this liquid water at 100 degrees Celsius turn into vapor, all of it. That's the energy you will need. But also, guys, let's imagine that this is also 1 kilogram of water. And also notice that the energy, you're adding all of this energy, but the temperature stays the same. So it's like, what's going on here? You're adding energy, but nothing changes in the temperature, but of course in the phase it is changing. Now these numbers, they're not just there because I made them up. These are actual numbers that have been found when you make these conversions, when you convert from the solid state to the liquid state and from the liquid state to the gaseous state. And scientists have found that you need this amount of energy in order to change your 1 kilogram of ice into water, into liquid water, because this is still water, okay? It's just solid water. And you need this amount of energy in order for you to change 1 kilogram of water into 1 kilogram of gas. You need all of this energy to change it. And this energy, it's not just a number for any amount. This is exactly the amount of energy that you need in order to change 1 kilogram of water, liquid water, into gaseous water. And also here, this is going to be the exact amount of energy that you need to change 1 kilogram of solid water into liquid water, ice into water. And these things, these numbers have a special name. We're going to call them latent heat of fusion and latent heat of vaporization. And of course, this is going to be for water. These numbers are not going to be the same. The fusion, latent heat of fusion for some other substance is not the same as for water. So that's why I stated here that it's for water. That's why we have this table. We have a latent heat table. Fusion, why do we call it fusion? Because it's like when you melt something. They also call it heat of melting. So when you melt, it's when you go from liquid to solid. And when you do fusion, you go from liquid to, when you melt, okay, when you melt, you go from solid to liquid, and when you make fusion, it's from liquid to solid, right? Anyways, what is important, guys, is that you need to remember that when you have heat of fusion, that's the energy that you require when you go from the solid state to the liquid state. That is fusion. Okay, when you have that situation. In heat of vaporization, you're going to need this latent heat, that energy that you get when you go from the liquid state to the gaseous state. Now these numbers are going to be for water, but you have different heats of fusion and different heats of vaporization for other substances. For example, alcohol, for gold, for mercury, and so on and so on. Now there's something else that you need to check out here, because as you can see here, you have a smaller number here than over here. That's important. Why do we have more energy when you go from the liquid state to the gaseous state than when you go from the liquid state, from the solid state to the liquid state? Well, it's because when you have a liquid and you want to go to the vapor state, you require more energy because they are more separated. They're more far apart than when you have a solid. And we're going to talk about that in a while. But before we do, I want to show you also a table where we have specific heats. Now, the specific heat capacity, it's not going to be the same for liquid water, for solid water, and for gaseous water, which is steam and ice, respectively. And we're going to be using this information when we get into the problems. But I just wanted to show you this because we are talking about tables. So I'm going to show you this other table, which we will be using in a while, okay? So the specific heat, remember that? That's the C that you used in the equation of Q equals M times C times delta T. So this thing is going to be used when you are in the gaseous state, and this is going to be the Specific heat when you are in the solid state, and this one when you have the liquid state in water. And of course, you got different specific heats when you have other materials, but we're going to focus on water. And now that we're talking about water, I want to mention you a few things that are important about water and that you need to realize about it and to think about how wonderful it is. It's not just something that you use to quench your thirst. It's something that is very important for the environment, not just because it's going to be good for the plants and it's good for keeping the world humid and so on, but it's also going to be affecting how we have our climate and our temperature. It's very important, guys. So I'm going to take a minute to talk about water. And this has to do also with the previous class, but I'm going to add it to this part because you are more familiar with water. So one of the numbers that you need to memorize, that you really need to have clear, is this number. It's 4,186. That number is the specific heat of water, specifically when you have liquid water, as I showed you before. Liquid water, solid water, gaseous water, it's not the same. Different specific heats. But as you can see here, this number, 4,186, that number you gotta memorize. You gotta keep it there in your head. That number, as you can see here, it's the largest number of this table. And this is going to be also the specific heat that is greatest for any liquid. And this is going to be very good. It's very interesting because this is the reason, this could be one of the biggest reasons why most of the objects, most of the living creatures require water and are made up of water. Water is awesome. I want to show you a few things about it. Well, the thing here about specific heat having such a big number for water is that, as you remember before, as I told you in the other class, when you have a bigger number for specific heat, it means that it requires more energy to change. And when you have a specific heat that is lower, it's not going to be resisting so much the change in temperature. So that means that when you have a very low specific heat, for example, let's say gold, or for example, what else do we have here? Gold has a very low specific heat. So that means that if you increase the temperature, the gold is going to be changing its temperature faster than, for example, iron. And if you change the temperature at that same rate, the water, it's not going to feel so much change in its temperature. So as you can see, if you increase the energy, the gold is going to be changing its temperature more than other substances from this table. But water stays the same, and that's going to be great. That's great. And this has to do with the bonds that you have between the molecules of water. The bonds, I want to talk about bonds more in a while, but right now I'm going to show you that these are going to be like connections between molecules of water, and this is the reason why we have such a high specific heat when it's liquid water. But when it's solid water or gaseous water, it's not so high. So when it's in the liquid form, that's when we get those advantages. Well, water has a lot of great characteristics that are going to be used for many things in nature. This is the reason also, well, when it's solid water, the density changes and it has a structure that is very crystalline-like, like a diamond crystal-like, and it's gonna change its density. It's a whole story. It's another story, guys, but I just want to show you something that is very important right now. For example, it says right here the specific heat of water is the greatest of any liquid, and that's the reason why it takes more time to heat water, and it also takes more time for it to cool. Okay, oh, that's what it's saying right here. And also, guys, here it says that when you have sand, that sand is going to be getting hotter first than the water. That's why when you are at the beach and you get your feet burnt, when you go to one of those beaches where you have high temperatures, well, you're going to look for the ocean water to cool your feet off, because the water doesn't change so much its temperature as does the sand. So that's a great advantage. But you know what? It's not just for when you're going to the beach, because also this is going to be helping the environment to stay at a constant temperature. So due to water and its uh, presence in everything, or pretty much everything where there is water, that's going to be making it stay at a regular temperature. So it's going to be resisting change in temperature. That's why the specific heat capacity is very high, and that's the reason. Well, maybe that's the reason why everything is made up of water, right? Um, if it wasn't for that reason, imagine that we were not made up of water, because you are made up of 90% of water, I believe, or 80%. Got to ask your biology teacher about that one. But imagine that you were made up of gold. If you were made up of gold, that's bad. That would be a bad situation for you, because if temperature changed a little bit, you would feel really cold or really hot. But no, you're made up of water. You don't have to feel high changes in temperature. You stay at a regular constant temperature. That's why water is so awesome. And also, going back to this environment and climate discussion we're having right now, if you go to a place where you don't have so much water, let's say a desert, you know what happens with the temperature? At the daytime, it's very hot, 38 degrees Celsius. That's incredibly hot. This is pretty much what you have, for example, at the Sahara Desert. And also at night, you can get very low temperatures in the same season. So in the same 24-hour lapse, in this part of the world, you get very high temperatures, but also at the night, you get negative temperatures, very low temperatures. Why do you have so many drastic changes? Because there's not so much water. But if you live close to a place where you have lots of water, the temperature stays very regular, stays very constant. And that's why if you go to, for example, Mexicali, where you have a desert-like condition, you got drastic temperatures. But if you go to, let's say, Playas de Tijuana, let's say, I don't know, let's say, for example, that you get very regular temperatures due to the water around you. All right, it stays constant. I'm not saying that it's colder or hotter. I'm saying that it stays constant during the most parts, during the most of the day, and during the whole 24-hour cycle of a day. Anyways, this is also let's continue also with this discussion. When you go outside and it's cold, your internal temperature stays the same due to the high specific heat coefficient that water has, because you're made up of water. So when you go to a place where it's very cold, yes, you will feel cold, undoubtedly, but your body doesn't change drastically in temperature. It's gonna take a while for you to change the temperature. And that's why many people can go into the cold and they're not going to feel so bad, because they keep their body temperature regular. But after a while, they're going to get cold. But this is due to the high capacity of water. So that's great. That's water, guys. So yeah, guys. Thanks, water. All right, let's continue with this discussion. Let's talk about what happens when you take a solid at 0 degrees Celsius and you want to change it to a liquid. Well, you need to add some energy. But what happens at the molecular level? Let's make a zoom here and let's imagine that we have some molecules of water. This thing here, this circle represents a molecule of water. It's made up of H2O, so imagine that inside this little sphere thing, there's a hydrogen, two hydrogens and one oxygen, and so on, okay? So we have here one molecule of water, and here's another molecule of water. There's going to be a bond between them, which we called hydrogen bonds, but that's another story for another time. What is important, guys, is that these bonds, these chemical bonds, hold together molecules. And when you have a solid, these bonds are going to be stronger than when you have a liquid. So these bonds, they work like, let's suppose, a chain. Now these chains, they're holding people together or holding these molecules together. So if you have chains in your hands and you want to take them off, what do? You gotta use some energy. And to use that energy, all of that energy is going to be used up to break the chain. So that's the reason why the temperature doesn't change, because this energy that you are using, it's not going to be used to make these molecules move around. This energy is going to be the least energy enough to make this chain break. That's the reason why the temperature does not change while you're going from the solid state to the liquid state of water. And after you break the bond, you don't have any bonds anymore. These molecules of water, they're free to flow. They're going to be moving all around. And they don't have any bonds anymore. Well, actually, there are some bonds between them, which is very important also, but they're not going to be as strong or with the characteristics that you have when you are in the solid state. So that's pretty much it, guys. All the energy here is going to be used up to break the bonds, but not to make them move around. The energy is going to be used, this latent heat energy is just going to be used to make a transition between the solid states and the liquid states. Alrighty. Now, with that in mind, we're going to have this chart, which is very useful when we solve some of the problems that I'm going to give you in a while. And what do we have here? For example, guys, we got to understand what's going on here. This is going to be very useful, guys. So we have here in this axis the heat supplied. That's going to be the Q, how much energy you use, how many matches you use, how much energy you put in your oven, for example. And on this side, you have the temperature axis. So how does the temperature change as you add heat? Okay, so let's imagine here that we have a solid of water. We've got an ice cube. And this ice cube, it's gonna have a temperature that is below 0 degrees. Maybe we're not accustomed to think about below 0 degrees Celsius, but we can have ice cubes that are colder than 0 degrees Celsius. So let's imagine that we are here at negative 50 degrees Celsius. You add energy. What happens with the temperature? It's increasing. You add more energy, it increases. And when you reach 0 degrees Celsius and you keep on giving it energy, that energy is going to be used up to change the solid to a liquid. That's why we have these uh, horizontal parts of the graph. This is not going to the vertical or downwards. I mean, going upwards or downwards. It's staying at the same height because the temperature stays the same. It doesn't change. That's why we have this zone. And then after a while, after you change all of this solid into a liquid, the heat that is going to be used, it's not going to be used to change its phase, but it's going to be used to change its temperature until you reach 100 degrees Celsius. And then after that, you're going to need some more energy. Remember that amount of energy? It's 2,300 joules. And over here was this section from, watch out. This section from here to here, it's 303,000 joules. Not so much as over here. So we have more energy over here than what you have over here. But the temperature, it's going to remain at 100 degrees Celsius. That's why it's like this, because the energy that you place here stays constant. That's great. Now what happens after that? When you change all of this liquid into a gas, here it is, that's a gas supposedly. Well, the energy is now going to be used to change it into a gas with a higher temperature. So that's why we have this line that is going in this direction, going upwards, because the energy that you place to it makes the temperature increase. That's what you have right there. Alright, so this information is going to be very useful, and something else that you also need is going to be the formula to solve these type of problems. The formula for latent heat, it's this one. It's very easy. Actually, this is pretty much the same as the other formula that you had before. Q equals M. See this M, right? Mass times, but instead of the L, you used to have the C and the delta T. Because you needed to know the heat capacity and also how much temperature you want to change. So it's basically the same equation, but now it's for when you have a change in the phase, and it's going to be given not by the specific heat, but by the specific latent heat, or the latent heat, whatever. Okay, so of course this equation, as most of the other equations, require mass given in kilograms, and the latent heat is going to be joules over kilograms. That's what this is saying. And this Q is just heat change. That's going to be given by joules. That's what you have right there. All right, let's do a problem. Let's say that we have an ice cube with a temperature of -30 degrees Celsius. That is the temperature, and you want to change it to a liquid, but not just any liquid. It has to be at 3 degrees Celsius. All right, and that ice cube, it's a regular ice cube having a mass of 208 grams. You want to know how much energy you're going to require to go from this very cold ice cube at -30 degrees Celsius to a not so cold but yet very cool amount of water, or bunch of water, right? What do we do there? What are we gonna do? Well, first of all, I'm gonna show you this chart. All right, we're gonna be having this chart to visualize what we need. Okay, so we have that ice cube at 30 degrees Celsius. Oh, I meant to say -30. -30 degrees Celsius. And it's right there, -30 degrees Celsius. And we know its mass, 208 grams. Of course, we gotta convert it. We gotta change it to grams, and it changes to 0.208. That is going to be the amount of mass in kilograms. Now we need to know how much energy is required to go from -30 to +3 degrees Celsius. In between the -30 and the +3, which is about here, and this -30 is about there, we have this section, which is the amount of energy that you require to convert this solid into a liquid. So basically what we need to calculate is how much energy you require to change from -30 degrees Celsius to 0 degrees Celsius. That's what you have right there. And then you also need to calculate how much energy you require for this amount of mass to convert it into a liquid, which is this formula. And then we gotta find the amount of energy to change that puddle of water at 0 degrees Celsius to a puddle of water with a temperature of 3 degrees Celsius. What do we do? What do we do? What's next? What do we have to do? Well, it's gonna be a three-step problem. Okay, is that what I just told you? It's right there. We gotta do these 3 steps. The first step is to calculate the energy from -30 to 0 degrees Celsius. And we're gonna use this equation that you are, I hope, very familiar with. There you go. That's the equation for heat. When there is a change of temperature, how much heat you require to make that change of temperature. And I'm gonna apply it to this case, to this section. And we know that the mass, it's 208 grams, and we're going to use the heat capacity. But watch out, this heat capacity is not going to be that familiar 4,186. Nope, no, because this is ice, solid water, ice, guys. And as you remember from that table that I gave you a while ago, ice is 2090. 2090, not 4186. This is for liquid water. This is for solid water, also known as ice. Okay? All right. So I gotta calculate that. That's what we have right there. And also notice, guys, that you're gonna go from -30 to positive. Well, not positive. 0 doesn't have a sign. It's just 0. From -30 to 0. So my final temperature is going to be 0, and my initial temperature is going to be -30. So that's why I placed it in this order. The order is very important, guys, because it's going to tell you if the energy is going to be positive or negative. When you get a positive energy, it's because it's going to be receiving the energy. When it's negative, it's releasing the energy. So that's important, guys, because the other 3 results have to be also of the same sign. They all have to be positive. But if you confuse these guys, maybe you can get a negative. Maybe not. Maybe you'll be lucky. Maybe you'll be lucky, but maybe you won't. Who knows? You gotta be not leaving things to chance. You gotta be careful. So you gotta do TF minus TI. TF is gonna be 0. TI is gonna be -30. That's where you start. This is where you start. This is where you end. So going from -30 to 0, you got to put first where you're going to end up, the 0. So it's 0 minus -30. That's why this becomes 0 plus 30, and then positive 30 times this will give you this amount. Alrighty, what's next? I gotta use that new formula that I gave you a while ago. Q equals mass times specific latent heat. And the mass, it's the same mass. It's the same. It's not changing. The mass, the amount of particles that you have of water, of H2O when it's solid, and then when it changes into a liquid, stays the same. It's the same mass. So I can't change this 208 grams it's gonna be the same amount. So this M and this M, same deal. And also, of course, I gotta change it to kilograms. That's why it's 0.208, not 208 like here. It's 0.208 kilograms. This is in kilograms now. I didn't place the units because we don't have so much space, but you guys be careful. Alrighty, I'm just gonna put the unit at the end. And this latent heat, which one should we use? That number there, I just didn't pick it up out of chance or randomly picked it from this table. No. I used the heat of fusion, not the heat of vaporization, because this is the one that you need. This is the energy that you need when you go from the solid state to the liquid state. That's what you have right there. Okay, so that's the amount of energy that you require to melt an ice cube of 208 grams. That's what we have in this step, step number 2. Let's go to step number 3. And we want to go from 0 degrees Celsius to 3 degrees Celsius. So what you have to do there is you gotta get the change of energy. You gotta get how much energy you require in order to go from 0 degrees Celsius to 3 degrees Celsius. So the final temperature is the final temperature is 3 degrees Celsius, so you get 3 right there. And the initial temperature is 0. So that's why we have 3 minus 0. That's going to be 3. And watch out. This specific heat, it's not the same as this specific heat, because this specific heat is when you have a solid water. When you have solid water, guys. But this one is when you have liquid water. So that's why the specific heat is not the same as over here. It's this number. It's 4,186. And just for reference, I'm going to show you this table again. The water is having this, the liquid water. This should be saying liquid water. 4,186. And this should be solid water. 2090. That's why we got different specific heats, and that's the reason we got those results right there. Okay, that result. Now what's going to be the next step? I'm not done yet. We got these 3 steps, but there's one more extra step. And the extra step is going to be, of course, you got to add all the energies. Add all the energies. Oh, come on, spelling. It's in English. Okay, we gotta add all of those energies, and that's going to be the amount of energy that you require to go from -30 to +3 degrees Celsius. You gotta add the energy when you go from -30 to 0 degrees Celsius, the amount of energy that you require to melt that ice cube, and when you are at 0 degrees Celsius, and also the amount of energy that you require to make that puddle of water into a puddle of water with this temperature. And all the energy that you will require is going to be this amount. So you got to add them. Now here's another problem. Now this problem has a gas of water. It's vapor. When it says vapor, you're going to assume that it's water. If they say something else, if they say it's a gas, you need to check out what substance it is. But usually when they just say vapor, they say they are assuming that you guys know that it's a gaseous, it's gaseous water, right? Okay, so we have water, water that is in the gaseous state, and it has a very high temperature of 140 degrees Celsius. Because of course you guys know that after 100 degrees Celsius, you get vapor, you get a gas. And water at 140 degrees Celsius cannot remain as a liquid. So that's what you have right there. That's going to be the temperature of the gas, the initial temperature. But then you're gonna be placing it inside, let's say, a refrigerator, and it's gonna be losing energy. You're gonna be taking energy off of it. What's gonna happen when you remove energy from an object? Its temperature diminishes. And this thing, when you place it inside the refrigerator, the temperature is going to be lowered. So it's going to be changing to negative 10 degrees Celsius. That's the temperature that you have right there. Okay, and you want to go at negative 10 degrees Celsius, so that means that it's going to turn into an ice cube. Going to be changing all of that vapor into ice. And you just have 50 grams of ice. 50 grams of ice, 50 grams of liquid water. That used to be 50 grams of vapor, or water in the gaseous state, of course. Okay, so this is going to be pretty much the outline of our plan to solve this problem. We are at 140 degrees Celsius, and we have this temperature that is very high, 140 degrees Celsius, and we're going to change it to negative 10 degrees Celsius. 10 degrees Celsius over here. So we're going to go from all the way over here to all the way over here. Okay? What do we do? This is going to be the outline. So I'm going to use the energy. I'm going to get the energy to change, or how much energy is going to be released when you change the vapor at 140 degrees Celsius to 100 degrees Celsius, from all the way over here to all the way over here. That's what this is saying. And then the energy that you have when you transform that gas into a liquid, which is this part. You're going to need the latent heat for that. And then the next step is going to be all the energy that you require to change that puddle of water of 50 grams to a puddle of water at 0 degrees Celsius, from 100 degrees Celsius to 0 degrees Celsius. And then when you reach that part of that section, that temperature, you're going to have to know how much energy will be absorbed when you change that liquid into a solid. So you lose energy when you go from from a solid state to from a gaseous state to a solid state. You lose energy, because think about how much energy this thing has. This gas, it's all around. It's moving upwards, downwards, left to right, everywhere. So that gas has a lot of energy. And when you increase its temperature, it has even more energy. But when you make it into a solid, all that energy is going to be lost. So it's like when you settle down, when you're dancing around and then you settle down, then you go to sleep. That's what happens with these molecules. You're going to have less energy. And what happens also with the temperature, it's going to be diminishing. And also, guys, you're going to need to finish this outline, the step 5 is going to be changing the temperature from 0 to negative 10. You got to know how much energy you require. Then, of course, at the end, you need to add all the previous energies that you calculated, which is going to be the amount of energy that you require in order to change the 140 degree gas into the negative 10 degree popsicle. Okay, first step. What do we do here? Okay, remember it's the same formula. Mass times specific heat times the change of temperature. This is the target. It's 100 degrees Celsius, TF, and this is TI. TI, it's 140, so it's 100 minus 140. And here, I gotta use the specific heat of not just water, but steam or gaseous water. That's what we have right there. And that's gonna be the first step. That's what we did right there. And of course, the mass has to be changed to kilograms. So we gotta divide from by 1,000. Oh, you know what, guys? Made a mistake. Just realized it. I made the whole problem for 500 grams. So I'm just going to change it right there. It's 500 grams. That's what I do. I'm going to change it to 500 grams. And when you change 500 grams to kilograms, all you have to do is divide by 1,000, and that's why this is going to be 0.5. I did it for 100, but it's for 1,000. That's what I meant. Well, you guys know what to do there. I mean, you've been changing. This one is correctly changed to kilograms because you had 208 grams and you changed it to 0.208 kilograms. That's perfect. But this one, let's take it as 500 grams. So I'm going to change that really fast. There you go. Let's change all of this. There you go. And let me change it really fast. Come on. I'm going to do this really fast. Not going to take long. There you go. Okay. Going back to this. Next step. Oh yeah, also something else. Notice here that the sign is negative. Why is it negative? Because that vapor is losing energy. It lost energy. It's not gonna get more energy. It loses energy because when you lower the temperature, it's because not just lowering the temperature, you're losing energy. That's what really happens when you lower your temperature. And then after that, we gotta use the latent heat formula, the energy that you require in order for you to change the gas into a liquid. That's why we used this amount in this case. And I gotta multiply by how much mass we have. So we multiply that and we get this amount. Of course, this is gonna be negative. That's negative right there. And this one, it's gonna be the next step, how much energy you require to change the 100 degrees Celsius water into a puddle of water at 0 degrees Celsius. And we gotta use the specific heat of liquid water, not the vapor state or the gaseous state of water, which are different, of course. So you gotta watch out. You gotta put that amount when you have liquid water. And of course, it's the same mass, and we gotta go from TF minus TI. So TF is 0 because you're going from upwards to downwards. From 100, you start at 100 and you end up at 0. So it's gonna be 0 minus 100. And that's gonna give us a negative number. That's very important, guys. In this case, when you are going from a high degree Celsius, or from a high number to a lower number, all of the energies that you have here, all of them have to be negative. If one of them is not negative, then when you add up all the Q's, you're gonna have an error. So you gotta watch out. Okay. Oh, wait a minute. Now what's next? We gotta get the energy that you require in order for you to change that liquid water into the solid water. There's not gonna be a change, okay, in temperature, but we got to calculate the energy, and it's going to be given like this. Now the formula, the original formula, there's no way to get the sign. That's why you got to put the sign. When you know that you're going to go from the solid state to the liquid state, you got to put it as, when you go from the liquid to the solid, you're going to be losing energy. That's why you got to put a negative sign. But when you go from the solid to the liquid, you need to add energy in order for it to change into that state of energy, and into that state of matter where there's more molecular energy, kinetic molecular energy. And of course, well, what's next? I gotta get the energy when you go from 0 to negative 10. So when you do that, negative 10 minus 0, this is the final temperature, this is the initial temperature, so it's going to be this minus this. And specific heat, it's going to be 2090. That's going to be the specific heat for the liquids, for the solid state of water. So when we multiply this, we're going to get a negative number. And what's next? What do you have to do next? You guessed it, you got to add all the energies. So there you go. That's what you have right there. And we get negative this amount. And this number is going to be negative because that vapor lost a lot of energy in order for it to become that popsicle. That's it, guys. You have a great day. I'll see you later.